So, welcome to the third day of the meeting. And the first talk would be Dr. Farhad Habib giving the second of his two lectures on AI. And today I understand that he'll be talking about the more recent developments. So, Farhad, please go ahead.
Okay, thanks, Uttara. So yesterday I gave an overview of many parts of machine learning and AI, particularly as it related to discriminative approaches to machine learning and when discriminative and regression-based approaches. So today I'll take a slightly more recent view of machine learning, and we'll talk about generative AI. So as the name implies, generative AI, it's about generation of new kinds of content. And as you might have heard, it's like taking the world by storm, partly because of all the possibilities that are available from it. So in a way, it has enabled people to do things like create novel things without let us see how generative AI works and how generative AI models or generative models in general work. And I'll try to take a somewhat less math intensive view of these processes. So to give an overview of my talk, we'll talk about generative models, a little bit of history of these models, and we'll then talk about autoencoders, diffusion models as they developed in time, finally ending with transformers and large language models. So what are generative models? So generative models aim to generate new data points similar to a particular training set. So for example, a model, for example, a model that takes an image of a cat and outputs the label cat is a discriminative model or a classification model. So essentially what it is doing is taking a certain data point and mapping it to a particular class. What a generative model would do instead is that it would take a label, for example, say a label like cat, and generate a corresponding image of a cat. So during the training process, what we aim to do with a generative model is that it should learn the distribution of data. That is, it should be able to look at the kind of data that it has been given and be able to generate novel data points that are similar to the data that it has seen. So it should not just replicate, it should not just replicate what it has seen, but be able to generate novel content, but that novel content should be from the same distribution. So it should be able to generate unseen instances by learning from the data set. And generative models can be used in a large number of cases. So they can be there you can use generative models to generate data points, but they're also used in image, text, and other kinds of creative fields. So let's take a look at a very, very simple generative model. Can you take a linear model and turn it into a generative model? So yeah, it's quite possible to do that. So essentially, a normal linear model is you take a set of data points and you do a best fit and you get a particular linear model that is a representation of the data points that were given to the linear model. Now, from these data points, you can estimate the parameters. For example, if there is an error around this best fit line, you can take the error of these data points and find out what's the mean, what's the variance of this error. And what you could do is then you can generate new data points by sampling from these feature distributions. So essentially, let's say if the error is a Gaussian, if the data points have an error that is normally distributed with a certain mean and variance, you could generate a random variable with the same mean and variance and put it along the line and add this random error that you have generated, and you would get a new set of data points that follow the same distribution that the original set of data points from which you had learned this particular distribution. So you could see that you have created a generative model that learned from the distribution that was given to it and would be able to, essentially, if you were to take the new set of data points, you would be able to get the same model that generated the original set of data points. And this can sometimes be quite useful when let's say you would like to release data that follows a certain distribution, but you cannot release actual data, for example, because of privacy concerns or uh, not having rights to distribute a particular data set and so on. So in that case, what you could do is you learn from a particular data set and you generate new data which has the same distribution, and you can release it so that other people can learn from the data, run experiments on it, and so on, without the original data being exposed. Okay, so this is an example of an extremely simple generative model. Now we'll go on to some other kinds of models that are a lot more complicated than this simple model that we just saw. So just to give a brief idea of the journey of generative AI models, the main point where we might think of starting with is autoencoders. So autoencoders have a longer history, but in 2013, we saw the development of variational autoencoders. And I'll spend a little bit of time on variational autoencoders in this talk. Then in 2014, Google's Dr. Ian Goodfellow came out with generative adversarial networks. And these were very exciting for several years. A huge number of variants of generative adversarial networks came around that were optimized for a lot of different use cases. In 2017, the big paper called Attention is All You Need came out, which introduced transformers. And that has been the bedrock of a lot of generative AI following since then. So in 2018, we saw the release of the first GPT. 2019 was GPT-2, which at that point was held back from public release for quite some time because it was actually said like it might be too dangerous to release it into the wild. But then in 2020, we saw GPT-3, and lately we are now working with GPT-4 and later models. These are all, the GPTs are text-based models, but on the top here are Midjourney, Imagine, Stable Diffusion, which are all generative image models. We'll talk a bit about them as well. And now we have a large range of generative models that are accessible to everyone. And I think even in this room, I would think that a fairly large number, a fraction of you, would be using generative models in some form or the other, be it ChatGPT or Google Bard or many of the other cases. Okay. So let's start with autoencoders. What are autoencoders? So as the name indicates, an autoencoder is a neural network that encodes data to itself. So what it does is it essentially is trained to copy its input to its output, but with a bottleneck in between. So if you look at the top neural network-like representation with the two kitten faces on either end, what this network is doing is taking in an image and passing it through a small bottleneck layer. So you can see that, let's say, you have a large number of data points going in, and you have the same number of data points going out, but in between, the number of data points is very small. So what the network has to do is to find a compressed representation of this data. And once your network is trained, essentially what will happen is that the network would have learned an embedding that represents the data that it has been trained on. So essentially, what the network is learning is a compressed representation of the data. So to give a slightly non-technical idea of what embedding or a representation is for example, let's say you can take an image of a person, and the image of a person is a fairly high dimensional representation of the person, because every point in that image it can take a certain number of values. So it's a very large, I mean, it's something that has a fairly high, large amount of information representing it. But you could also compress this information down to something like, let's say, the distance between the eyes of a person, the length of the nose of a person, what color the person is, what color the eyes of a person is. And just by that, you get a much more smaller representation of the same image, but it's not an exact representation. But you might have captured the salient features of a person's image. So what you've done is you've taken a compressed output, and this is a lossy compression, so you won't get the same visual of a person back, but you can still describe the person in a far lesser amount of information than a image would have described. So so this brings us to like what is an embedding. So an embedding is essentially a low-dimensional vector. So one of the most commonly used embeddings is PCA, principal competence analysis. So the essential idea of an embedding is that it has fewer dimensions than the object that the embedding is representing. And essentially what an embedding algorithm does, so for example, what PCA does is it maps a point in the ambient space X to its embedding space, to its embedding edge. So the embedding is much, much smaller than the object that you start with. So the main point, so let's come back to autoencoders. So how do autoencoders learn? So autoencoders are essentially designed to learn the salient features of a data set. So what we have is that, as I was saying, that the information in an autoencoder passes through a bottleneck. So an autoencoder is, just as we learned in yesterday's talk, it's essentially a neural network with a large number of, with neurons in the beginning and the same number of neurons at the neurons in the input and the same number of neurons on the output side. And in between these, you have a series of hidden layers with a hidden layer in the middle that is, let's say, a much smaller layer. And the idea is that as information passes through this bottleneck or the smaller layer, the hidden layer in the middle would learn a representation of the data set that is much more, it's learning the salient features of the particular data set that it has been trained on. And the interesting thing about autoencoders is also that in case your decoder is linear, that is all the activation functions are linear, then and the loss function is the mean squared error, the autoencoder simply reduces to the principal components analysis of the data set that is being given to it. So you'll get essentially the top k principal components depending on the size of the bottleneck layer, which would be k here. And in case, that's with a linear set of activation functions. If you have nonlinear activation functions, then the autoencoder can learn more powerful nonlinear generalizations of PCA. Okay, I'll take a pause at this point, and if there are any questions, I'd be happy to take right here. Okay, so autoencoders can learn the hidden representation of a data set, but they're not very convenient because the representation that you learn from an autoencoder is not, might be gappy and does not necessarily have a particular distribution. So the next step that people came up with was variational autoencoders. So what variational autoencoders is that you not just have a hidden layer, but you also impose a condition on the what kind of distribution the points in the hidden layer have. So an autoencoder's training objective is mainly to minimize the reconstruction error. That is, you try and reconstruct the original data set as closely as possible. With a variational autoencoder, what we try to do is to minimize the reconstruction error plus regularize the latent space. So what I mean by regularizing the latent space is that we want the distribution of the points in the hidden layer or the middle layer to follow a certain distribution. Usually we want that to follow a normal distribution with a unit variance. So what we have is we impose the condition that the points in the hidden layer have a normal distribution, and that can be quantified by using the KL divergence. So essentially, KL divergence can quantify the difference between two different probability distributions, and what we want is that distribution to be as close to the normal distribution as possible. So what?
Sorry to interrupt you.
Yeah.
mm, so in case of a normal autoencoder,
Mhm.
you're saying that it's making it smaller. The representation is smaller, and so the
Mhm.
information required is less. But
Mhm.
if I consider the hidden layers activity as well as the weights, so
Mhm.
uh, I can say that the information is sort of distributed in the activity of the hidden layer and the weights as well, right? Because the input didn't have any weights to start with.
Yes. So the
So,
weights are learned by the model. So what what we are seeing is that the data itself can be represented just using the inputs to the hidden layer, and the model can reconstruct the data given the weights that it has just by using the what the data entered in the hidden layer itself. So the parameters of the model are a part of it, but the data can be represented just by the hidden layer itself.
all right, thanks.
Okay. So in variational autoencoder, what we have is that we impose an additional condition that the points in the hidden layer also have a certain distribution. Usually the distribution is a Gaussian distribution. Uh, Now, the good part about that, and now the interesting part about that is that now we have a smooth representation of the uh, distribution of the input within this hidden layer, and you can sample from this distribution. So now that we have imposed that the hidden layer has a uh, normal distribution, you can generate new unseen data by sampling from the latent space. So essentially, we can sample from a Gaussian distribution with a given mean and variance, and plug those numbers into the hidden layer, and we can get a reconstruction of the data set, which has the same distribution, which is coming from the same distribution as what the network was trained on. So this is an example of a fairly powerful kind of generative model here. Okay. So, for example, this has been used to generate images. So you can see that these are images of people that do not exist. These are not as good as some of the methods that we'll discuss later. But the interesting part is that you can also apply different kinds of conditions. So you can have different neurons in the hidden layer correspond to different parts of an image. So you can condition the training in such a way that you could have a particular neuron, say, encode how smiley a person should be, or whether it would be smiley or frowny, or so on, and things like that. So you can have the variational autoencoder be a lot more versatile than a normal autoencoder. Since a variational autoencoder is fairly simple, I wanted to show you how you can code one up, and we can look at how a variational autoencoder would work with a small training data set called an MNIST data set. Let me zoom into my screen. Are you able to see my window here? Okay, let me close this. Okay, so what we'll do in this particular exercise is create a small autoencoder, a variational autoencoder, and train it over the MNIST dataset. So for those who are not familiar with MNIST, I'll give you an idea. So MNIST is a set of handwritten digits dataset. I think it originates from the US Postal Office, which was interested in reading zip codes on envelopes. So you have a large number of digits that are handwritten, and we would like to classify them between 0 and 9. So you have 10 possible categories. And here I've shown this top row here shows what kind of digits you might expect to see. So since they're handwritten, all of them have certain variations, but you would still expect them to uh, so you can easily classify them, except that sometimes they're difficult, but largely they're easily classified as one of the 10 classes from 0 to 9. Now let's see if we can train a small neural network, a small autoencoder to be able to reconstruct these images, or like sample from the distribution of these images. So I'll not go too deep into all the code, but I want to highlight certain parts. So this is the encoder part of the neural network. What it does is it takes in a image which is 28 by 28 pixels in size, and it's flattened into a single vector, which is 28 by 28 in size. Then we pass it to a dense layer, which is essentially another neural network. I mean, another layer in the neural network. We've chosen 128 neurons here, and the activation that I've selected is the ReLU activation. And then I straight away have the middle layer or the latent dimension here. So in this case, I've left it as latent dimension, which I can vary to see what's the effect of changing the latent dimensions. Okay, this lets us sample from this layer to see what the mean and variance of this of the hidden layer is. Then we have a decoder, which is exactly the same. So the decoder has 128 neurons to start with, and an output layer, which is 784, which is 28 by 28. And this reshapes the 784 length vector back into a 28 by 28 matrix. Okay, and here we define the loss. So we have the KL loss, which is how far away from a normal distribution this is. And we have the regular loss, which is the mean squared error. And this is code for training and so on. So let's see how far we can get with a latent dimension of just 2. So a latent dimension of just 2 for all the digits that we encounter. So I will start training my neural network. So in this case, let's see, hopefully it'll work well. So I'm training it for 30 epochs, and we can see that it starts with a certain Kullback-Leibler loss, as well as the mean squared error. And the number of data points that I'm giving it are 938. So it has 938 different digits that are in the network, in the data set. It's not very large, so it may not generalize that well, but it allows us to do this training quickly. And I'm training it for 30 epochs. That means it's running over the same data set 30 times. And as you can see, like our training loss is going lower and lower. The KL loss is going slowly, very lower. The reconstruction loss is declining much more rapidly. Okay, so it's almost done, and it's done. So now we can, what we can do is we can sample from the latent space and see what kind of reconstruction do we get over here. So you can see that the top row is the data set that was given to it, the original images, and the bottom row is the images that are generated by the network. And you can see that it's not perfect, but we've still gotten quite a bit of the way through. And if we had trained more, or if we had a larger data set to work with, we would have possibly gotten better results. But some of the advantages of variational autoencoders are that they're reasonably fast to train because there's your neural networks, you can train them on GPUs and so on. And it works, and the results are fairly good, at least for certain kinds of data sets. Okay. Any questions here?
Sir, how do we choose the appropriate activation function between ReLU, sigmoid, or softmax?
That's a hard question. So most of the time, the activation functions are chosen by trial and error. For hidden layers and so on, often an activation function like ReLU or sigmoid works reasonably well. One downside of sigmoids is that at the edges of a sigmoid, the gradient is fairly low. So that means that the training can be slow. So one advantage of a ReLU is that its gradient is fixed. I mean, regardless of where you are on the ReLU. but it doesn't have, I mean, but because it has a gradient of 0 below 0, it doesn't, it sometimes may not train well. So there is leaky ReLU where you have a smaller gradient on the side below 0. So that works pretty well. For the cases where the activation function is fixed are the output layers. So for example, if we want the output to be a regression, then you would want something like a ReLU or a similar function so that the regression can output anything it likes. If you have a classification output, then if it's binary classification, you might want something like a sigmoid. If it's multi-class classification, then you would want something like a softmax so that you have a probabilistic output where the probabilities add up to 1 as you would expect them to. So that's how you would be able to select what kind of an activation function you would like. I hope that answers the question. Okay, so going to the next major development for generative AI was the development of generative adversarial networks. So these were a major thing between 2014 and 2018 or so, when a large number of different kinds of generative adversarial networks were developed for a lot of different use cases. So generative adversarial networks, as their name indicates, have two parts to them. One is that they're generative, and the adversarial indicates that the generative GANs, or generative adversarial networks, they work by having two neural networks competing against each other. So what you have is two networks. These are two independent networks. One is a generative network that generates a data set. Often it's an image, but it could be something outside of an image as well. And the other side is a discriminator, which takes in the output from the generator and tries to tell whether or not that image is fake. So, so what you have, let's say in this figure that you see on the right-hand side, is you have a generator. The generator takes in some random noise. It converts the random noise to a fake image. And there is a discriminator, and the discriminator is trained to distinguish between a real image and a fake image. And if the discriminator cannot tell real from fake, then what that means is that your generator has gotten good enough that the images that it is producing are as good as a real image. So this is the essential process of a generative adversarial network. And the generator's goal here is to produce data that is indistinguishable from real data. Okay, so how does it work? So for the generative model, the input to a model is noise. So essentially, you input some sample noise to the model, and the model converts that noise into some kind of data set. Usually, so the generative model is a neural network. It takes in some noise and it has its parameters, and the kind of noise given to it usually has a very high dimensionality. Essentially, then what you do is you take that output, let's say it's an image, you feed it to the discriminative model, and the discriminative model tries to figure whether it is real or fake. So how does the training for a GAN work? So GAN starts with training the discriminator first. So first what you do with the GAN is you start with a set of real images. So let's say you have a large bunch of real images and some other images that are not a part of the training, not a part of the training set. So you start by training the discriminator to be able to tell real from or the class that you're interested in versus the class that you're not interested in. Next, what it does is it receives real data from both real data from the dataset and fake data generated by the generator. So when training the generator, our goal is to maximize the mistake rate for the discriminator. So essentially, what you do is you reward the generator if the discriminator classifies fake data as real. So in order to train the generator, what we do is we take the discriminator's predictions on the fake data. That is, how closely does the discriminator, how closely is the discriminator able to tell that the particular data point is fake, and you calculate the generator's loss based on that, and you take that loss and then update the generator's weights accordingly. So as the generator gets better, you can also feed, if the generator gets it correct, you can also train the discriminator to update its weight in order to detect that a particular image is fake. But in general, these two training cycles are independent of each other. That is, you start by training the discriminator, then you start by, once the discriminator is trained, you fix the weights of the discriminator, and in the next step, you update the weights of the generator based on the discriminator's output of what the out like what it is classifying for the generator's output, and so on. GAN training, though, is a fairly hairy and finicky process. So one part is that the two networks should be balanced with each other. That is, if your generator is always, if your discriminator is very good, that is, it's able to tell with a very high certainty that the generator is wrong, then in that case, the generator simply stops learning because it doesn't have enough signal to learn back. So in that case, what would happen is that there's something called mode collapse, where the generator only learns limited varieties of data. Or it might happen that the generator figures out a particular mode in which it's able to pass through the discriminator. So a very few kind of samples start being classified as real, whereas everything else is false. So in that case, what happens is that the output distribution is not as general as you would like. You start seeing similar images again and again, which pass through the discriminator. A second thing that can happen is non-convergence. That is, the model simply does not converge very well. It keeps oscillating. So you find images going from one kind. Basically, you have images that are not good at any point. You find different kinds of issues with the image, and the output or the generated images or the generated data points cycle between two points, but not coming out as what you would expect it to happen. Hyperparameter tuning in GANs is essentially a lot of trial and error. So things like learning rates, you have to tune the learning rates so that the strength of the generator and discriminator is balanced. It's essentially a sort of equilibrium between two networks fighting against each other. And if as long as both of them are balanced, you end up getting good output. But if they're not balanced, you will end up with a mode collapse or other kinds of artifacts like that. Last point is that you require a large amount of diverse training data in case you want to learn, you want the GAN to learn realistic data distributions. So to start off with, the models were fairly, they were able to generate fairly small amounts of fairly small sized images, but rapidly people grew to make, improve the model generation process to generate fairly realistic and large scale images. So this is from one of the papers by NVIDIA, where they generated images that were 1024 by 1024 pixel sized. And you could see that these are pretty realistic images. If you look very closely, you can find artifacts which indicate that the model, that these are AI generated images and not real. If you look closely, you can see, for example, that ears might be mismatched. Eyes might occasionally be not exactly the same between two parts, and so on, because some of the longer range correlations are lost. So, but still, it's pretty realistic and good. I'll also show you some examples of what happens when a mode collapse happens. So for example, here you find on the top row, you find the same kind of image being generated again and again. That's maybe because this particular image or this particular type of image was able to pass through the discriminator where the discriminator decided that this was okay. And then the generator stopped learning, and so on for different kinds of images. So in this case, the GAN stopped converging as you would want it to. Okay, before I go on to the next section, any questions here? Okay, so the next part is about transformers. So this is one of the most
Question. So how do you train these GANs like this discriminator and the generator? Is it backpropagation or do you do something
yeah,
like
it's
a
backpropagation. No, it's
back?
backpropagation. Yeah, these are neural networks. So all neural networks are trained essentially through backpropagation.
All right.
Okay, so coming to transformers. So transformers originated from a paper called Attention is All You Need from a set of Google researchers, none of whom are at Google anymore. But ideally, since transformers have come into the realm of machine learning, we are seeing almost every problem that is out there has been, every large scale problem that is out there has been tackled with transformers very effectively. So they're seen in text, they're seen in images, audio, and lately they're being applied to video models as well. So what is attention? So attention in neural networks is essentially a mechanism that allows the model to focus on certain parts of the input data more than others. So essentially, so it's similar to how humans would react to, let's say, a noisy room where you're talking to the person opposite you, and you sort of tune out all the other people and focus only on the person you are talking to. So the way in which a neural network focuses its attention is having a like essentially it's another matrix in the entire set of matrices that comprise the neural network, where the weights of that matrix are also learned by data. So what attention is a way for the model to focus on specific elements in of the data that it's processing, and which makes the predictions better and generates much more coherent outputs. So I haven't talked about the other kinds of neural networks that preceded transformers. So networks like, say, recurrent neural networks or LSTMs. Some of the issues with those kind of networks, like recurrent neural networks, had a model where a model was able to focus, a model was able to take into account a series of data points, not just the initial data points. So essentially, it was looking at a certain uh, a certain number of data points in the past as well before it predicted the next state. So what attention changed is that these networks could look at the entire data set at one go, and to be able to do that, they are able to use attention to focus on which part of the data set being given to it is more relevant for the particular task at hand. So the way in which transformer models or large language models are trained is often something called self-supervised learning. So the way in which this works is you take a very large corpus of text. So for example, this might be text like Wikipedia, journal papers, conversations in a site like Reddit, and so on. And the task for the model is to predict, and what you do is you mask certain words out of this text. So for example, let's say you have the sentence, a quick brown fox jumps over the lazy dog. So let's say you randomly masked two of the words, and you ask the model to be able to figure out what the masked word is. And as you train over the model, it becomes better and better at figuring out what the masked word is. The interesting part about this is that when you do this over very large amounts of data given to the model is able to figure out all the kinds of rules that you would want it to learn about a language, or even about a set of languages. So in this case, the large corpus fed to the model, like let's say Reddit conversations, could be several tens of terabytes in size. And as you train the network, it learns what different words are. It learns how they are organized, and so on. And it's even able to figure out how it should, let's say, how it should generate the next word. So in that case, so what happens is that if you are able to feed any kind of sentence, the model is able to pick out very accurately what the next word or what the missing word in a particular sentence would be. The interesting thing that has happened about this is that people are now running out of text to be able to train their data sets on. So companies that have a lot of human written data sets are actually largely valued because of the value that these data sets contain. And another interesting thing that has been said about this is that right now what's happening is that a large amount of text that you're consuming, even in places like, say, Twitter or Reddit or any of these kind of forums, is written by AI. So you have a large number of bots that are actually putting in the text, which means that given that it's not human generated text, if you were to train on this text, you are basically feeding back on the output of the same model. So companies that have access to pre-2020 data have a sort of golden opportunity to license the data sets to various companies. So recently, as you might have seen, like Reddit went public, and its value is not so much in terms of what its users are doing now, but what its users did before. And some people have described pre-2020 datasets as, for example, the equivalent of low background steel in physics, where steel that was made before 1940 is called low background because it doesn't have radiation coming from the nuclear tests that have happened since then. So there is a certain advantage to having datasets that are definitely human generated. Okay, so another part that has been found when people trained large scale data sets is something that was described as people found several kinds of scaling laws, and they're called chinchilla scaling laws or other names, partly because these scaling laws came out when a particular model called the chinchilla model was being trained. But the main point about them is that what they found was that for a given was the ideal amount of training that you would need to do for a given compute budget and a given amount of data that you have. So generally what they found was that training models with more data and fewer parameters are more effective than training larger models with less data. And this contrasted with earlier beliefs emphasizing increasing model size. So one of the earlier beliefs was that if you keep increasing model size, and we have seen that model sizes have become extremely large in recent times. So previously, people would consider like a 1 or 2 billion parameter model as large. And now we know that like ChatGPT-4 is at least a 1.5 trillion parameter model. It's not public, and there are a large number of several hundred billion parameters that are publicly available as well. So what these findings propose is an optimal training regime, balancing the scale of the data set, that is the amount of tokens that you can give to the training data set, size of the model, and the compute budget that you have. And the fact that you need to, I mean, depending on the size of the training data set and so on, you can decide on an appropriate training model, appropriate model size using these scaling laws. So as I was talking about, there are a large number of models that are available to you. If anybody is interested here in this audience, I would certainly suggest that you can try out small models, small language models, even on a regular laptop. So something like, say, a 7 billion parameter Llama model or a Falcon 7 billion parameter model can be loaded on a 16 GB laptop with just a CPU, and it will still work reasonably fine. It will be slow, like as in you generate maybe a word every couple of seconds, but it's great for experimenting, and you can get an idea of how these models are trained, how you can fine tune a model like that. And if you have access to more compute, you can definitely like it's not out of the reach to have to be able to use your own 13 billion or even a 30 billion parameter model. Beyond that, you may want to have, let's say, a GPU or things like that. But up to 30 billion parameters, CPU inferencing is slow, but not unreasonably slow. Like you would be able to see a word every second or so. And here's the leaderboard on the site called Hugging Face, where a large number of open source models are available. People fine tune them, people train them, people compare them against each other. And you can see the models that are at the very top are now nearing almost as good sometimes as their closed source counterparts in many of the rankings. And the advantage of using your own model is that you're not restricted by what kind of restrictions are put by the ChatGPT or Gemini or other models like that, where oftentimes you run into like, I'm not allowed to do that or things like that. Okay. Any questions at this point? I've been speaking for some time. Okay. So I talked a bit about.
Sorry, I have a question. Yeah, so how do I actually interpret these rankings? Because, like how do they compare against, let's say, ChatGPT or other closed source models?
So there are a set of benchmarks. Like there are benchmarks like I think one is called BLE or Blue, where you give the model a certain set of questions and you look at the output and then you see how close the output is to what was expected from it. So that's how a model is judged as better or worse compared to another model. So for example, there's a bunch of tasks like, let's say, classification or inferencing or so on. And you just have a set of fixed answers and you try and see how close the model was able to get to the actual answer that it was supposed to be able to get.
So here in this chart image, you have some numbers at the right column, some average, something. Is it like a score? And then how do I interpret this?
So the score is, I think, averaged over a number of different benchmarks. And it's been averaged out in some way. So you have a set of benchmarks and you average out the score from different benchmarks and you rank them accordingly. So it's entirely possible that a model that is not as high in the rankings might do better for the particular task that you have at hand. Also, you can see the size of the models, like in all the top models are 72B, which are 72 billion parameter models here. If you go all the way down to the very last one, we see a 34 billion by 2 MOE. So MOE indicates a mixture of experts. So mixture of experts is a model that's a sparse inferencing model. So these are different techniques which are used to reduce, for example, inference compute costs and things like that. But the way you interpret the score is that a higher score indicates that it is in general doing better over a wide range of tasks, may not necessarily be better at a particular specific task that you are interested in. But that's how you would interpret it. I don't know all the benchmarks that go into it, but I know there are a few tasks related to things like translation, things like classification, answering regular questions around what might be expected for a language model to know things like, what's the capital of a country and so on. So it has a range of questions which try to make sure that the model is answering correctly or is
Right.
able to do text
Yeah, sorry.
summarization.
Yeah. And I just wanted to know, like, how do I compare it against closed source models? So are these numbers, are these rank scores available also for the closed source models?
Yeah, you can also run the benchmark on a closed source model. So you don't need to know the parameters of a model to be able to run, because you can give the same input to a closed source model and get its output and compare to what the actual output should be. So these benchmarks are available for closed source models, as well as if you desire, you can actually run the benchmark for a closed source model as well.
All right. Thanks.
Any other question? Okay. If not, I'll go to a entirely different. Yeah.
Sorry to interrupt. I have a question. So since inferencing can be largely significantly influenced by the amount of compute power, how can it be fairly judged among different models?
Inferencing is inferencing is largely a function of the number of parameters that are used to compute the output for a model. So it's what you would do is you would be able to, I mean, you can judge it in terms of a large model, like for a model like a 72 billion parameter model, it'll be all your parameters are being used. The cases where things become different is when you start doing special things with your model. So for example, mixture of experts. So that is one way in which I'm not as familiar with mixture of experts, but essentially a part of it is splitting the network into different components, which are so-called experts, and the model routes some of the computations to one expert or the other, depending on what the input is. And that way, not all the parameters of the model are used. So in case you have a large model like a trillion parameter model, which is split between a number of GPUs, you're not using compute on every single GPU out there. A second way in which inferencing costs can be reduced is, and this is very clever and is now becoming its own field of activity, is by quantizing the models. So if you look at the third from the bottom model, it says F16. What it means is that it's a floating point 16 model. But people have found that you can say reduce instead of 16-bit floating point representation, you can have an 8-bit floating point representation, or you could even have a 4-bit representation. So what that means is that the number of values that a particular weight can take are significantly reduced, but the model and the model's expressivity reduces, but maybe not by as much. So in that case, you can the amount of the total size of the model reduces drastically. It also reduces the capacity or the score of a model, but hopefully not by as much. So it makes it possible to run a large number of parameters on a smaller GPU, or maybe make it run faster or things like that. Another advantage of many of these quantized models is that there are techniques which are, and I didn't intend to talk about it, but since it's come up, I'll just give a brief idea about them so that if anybody wants, you can look them up in more detail. Is techniques called low rank adaptation, LoRa, or quantized low rank adaptation, that is QLoRa. So essentially, the idea is that if you want to fine tune a model, that is, you take a model and you want to fine tune it to a particular kind of domain that you have. So what that means is that these models are trained on general English text without any particular domain that they're targeted towards. But let's say you only want, you want your model to be much, much better at, let's say, medical knowledge. So in that case, what you would do is you can take the model that you have, which has been trained generally, and you'd give additional training data, which is coming from only the domain that you are interested in. And that means that the model weights would optimize themselves towards the particular domain that you are training it for, at the expense maybe of the larger domain that it is, of the general knowledge that it is ignoring. Now, that can be a fairly expensive process because you have to hold all the weights in memory. You have to compute the gradients. You have to pass. You have to add these. You have to do all the training and so on for the entire model, which is fairly large. So what techniques like low rank adaptation do is, if you remember your matrix algebra, the rank of a matrix is essentially how like the number of rows or independent rows or columns you have in a matrix. So let's say you have a large 72 billion parameter matrix, and you don't want to, you're not able to hold all those 72 billion parameters in your training. So what you can do is, let's say you take two matrices of a lower rank, which multiply to be of the same size as your 72 billion parameter matrix. Now, this will not be completely as good as as training the 72 billion parameter matrix directly, but you take two smaller matrices, which when multiplied, give you a 72 billion parameter matrix, and you only train these two smaller matrices, which can be much, much smaller because you are dealing with a low rank matrix. Now, in that case, you are still training these parameters, and it's unlikely to be as good as training the entire matrix. But because your space savings are so large, you can often get away with having a much, much smaller amount of compute to work with. So that is called low rank adaptation, LoRa, LoRa. And the quantized version, where you try and reduce the number of bits of your number of bits of the of the parameters that you're using. So instead of using the full 16-bit weights, you could use like 8 or 4-bit weights, and you can do another round of saving on top of that. So you can use a very large model, but quantize it. So these are some of the techniques that can be used to train these gigantic models, even with limited compute resources. Okay, so this was a digression. Any questions around here?
So I had a question, just in regards to attention that you spoke about. Is it the same as weights or is it different from it?
So attention is a type of weight. Like essentially, these are all matrices. So yeah, and these are trained. I mean, the weights are also not manually added in. The weights automatically come about as a part of the training process.
So are weights in relative to each other the input data, and attention implies weight given within that input data, a particular input data. Is it like that or is it different?
No, it is like that. So the attention weights would be like for the same for all data sets, but which weight gets valued depends on what the input data is. So for example, this comes in useful in case in case you have let's say a text stream coming in, which says something like, let's say a simple sentence like, John was in his office today. He forgot his coat over there. So now if you look at the second sentence, he forgot his coat. So he in this case refers to John in the earlier sentence. And the attention matrix is able to map like given a large context, it's able to accurately map what these different parts of a sentence refer to each other. So it would be it would be able to give a larger weight to John when you are looking at he in the second sentence. So that's how attention is able to focus on different parts of a sentence.
Thank you.
Okay, any other questions here? Okay, if not, I'll go on to another kind of model. The reason I brought transformers before diffusion models is that this connects to other kinds of models like DALI and so on, which I'll talk about, where where diffusion comes into a role for generating images. So what are diffusion models? So diffusion models are a class of models where the model learns a data distribution by iteratively corrupting the data and then learning how to reverse the process. So diffusion, as you know, is simply a process where you can take a data point and corrupt it using, say, a Gaussian noise. And eventually, like if you do it a large enough number of times, you end up with a pure noise. So the top row of image here indicates a forward diffusion process. So you start with a clean image, you add some noise, you keep adding noise until you end up with an image that is indistinguishable from the data. Now, what you want to do is to learn how to reverse this process so that there is given a noisy data set, you are able to recreate the original image back. So you have the reverse diffusion process. So the forward diffusion process, you add noise in a large number of steps. The steps can be as large as a few thousand or in that kind of a range. On the reverse diffusion process, what you do is you train the neural network to reverse the diffusion process and reconstruct the original data. And this process works pretty well. You can apply it to a large kind of different data types, for example, images, audio, and lately video as well, given enough compute. It does require a lot of compute, but an advantage of diffusion over GANs is that GANs are much more finicky about being trained. So you're requiring to train two different neural networks with different learning rates. You have to balance the learning rates. You often end up with things like mode collapse or other issues which prevent the network from generalizing as well as you would like. Whereas diffusion, being a much more cleaner process, is far easier to work with. So this is like briefly how you would train a diffusion model. So you start by corrupting the data with Gaussian noise over a large number of diffusion steps, and you turn your data into pure noise. And on the denoising side, or learning how to uncorrupt the image, you train the model to predict the noise that was added, effectively learning to denoise the data. Okay, so and the way the parameter optimization works is that the model parameters are optimized to minimize the difference between predicted noise and the actual noise that was added during the diffusion process. So diffusion by adding Gaussian noise is one of the ways. There was another like recent, as in about a year back, paper which tried to use a bunch of other kind of regular physical processes like Poisson diffusion, Poisson processes, and so on, to corrupt the data, and they found that it works well under different conditions. So this is only one of the natural kind of processes that adds noise. You can use other noise generating processes as well to create a generative model that is pretty expressive. So on the inferencing side, what you do is you start with pure noise. Once you've trained the model, you can start with pure noise, and you start denoising the data by predicting and subtracting the added noise at each step. And what the model has learned from the if you have trained the model on a large enough number of images, it tries to get back to an image that it has from the distribution that it has learned from. And the best part about diffusion is that you can do conditional guidance. So similar to how we could use variational autoencoders condition on different parts of, on let's say a particular feature, you can condition a diffusion model on additional inputs, like say text prompts or class labels, to guide the generation process towards a desired output. So this is how image generation models like DALL-E work. So I think all of you might have heard of DALL-E 2, and it's available via ChatGPT. Sorry, DALL-E 2 is, it's available via ChatGPT. And there are a bunch of other models like Imagine from Google and so on, which all work more or less on the same principle with a different kinds of training data sets and weights and so on. But what you have in this particular model is that you have a diffusion process that is conditioned on a text prompt. So let's look at briefly how that works. So to look at that, there is another model that I'll briefly talk about that is called CLIP. And CLIP stands for Contrastive Language Image Pre-training. So what the CLIP model is trained on is that it is trained to understand and associate images with different textual captions. So what they did was you took images which had a particular caption associated with it, and a bunch of captions that had nothing to do with the image. And they performed something called contrastive pre-training. So what contrastive pre-training does is it tries to maximize, to teach the model to distinguish between matching and non-matching pairs of data. So in this case, the matching part is in case the image is matched to a particular caption, and the second case, the image is not matched to a particular caption. So what contrastive loss does is it tries to maximize the loss when the difference is when it's different, and minimize when it is the same. So you present the model with pairs of images and the corresponding text captions. And for each matching caption that describes the image, the model's task is to predict which caption correctly matches the image among the set of possible captions. So that is the CLIP model, which associates, which learns a joint representation of images and their corresponding prompts. So this is like a high-level overview. I took this image from the paper itself. What we have is on the top part above the dotted line, let's say you have a text encoder which takes in a text prompt like a corgi playing a flame-throwing trumpet. And the image encoder on the other side, which has an image which corresponds to that particular image, which has an image that corresponds to the particular prompt or the text caption given to it. Now, below the dotted line, what happens is the text to image generation process. So once you have trained the model, your text embedding is fed to a diffusion prior to produce an image embedding. And what this does is that the diffusion process is, or the process of reversing the diffusion is conditioned on the caption that is given to the model. So what it does is it brings the image as close as possible to the text prompt that was given to it. And surprisingly enough, it learns very well all kinds of images, all kinds of nuances that you might expect it to learn. So for example, in this case, you have like and it can also learn things that it can also represent images that are not in its training set. So for example, something like a teddy bear roller skating on Times Square would not be one of the images that it has seen, but it would have seen enough people, enough images of somebody roller skating, enough images of Times Square, enough images of teddy bears, that it can put together a realistic image, synthesizing all these elements that are given to it. So for example, some of these images that are generated through the DALI 2 model is given here. Like for example, the top one is a high quality photo of a dog playing in a field next to a lake. And you can see that it has largely gotten everything correct. If you look very closely, you can see that it is an AI generated image because it shows certain things that are not physically possible. And for a long time, things like number of fingers or hands not drawn correctly and so on were an issue. But lately, most of those issues have been solved to the point where these images are gotten good to the point that it's very hard to tell whether it is a AI generated image or a real image. So, I mean, if you look very, very closely, you can still see certain things missing in AI generated images, particularly like sometimes things like fine structure of fingers or hands. Sometimes you might have, like, especially if hands are folded together or so on, the fingers can go off. But these would be solved at some point. Another thing that DALI 2 itself was not very good at was generating text captions. So if you'd ask it to generate text, it would generate something that looked like text, but it would not necessarily be what you asked it to generate. And that has also been largely solved with some of the more recent models from like Stability and so on. Another part that people discovered was that while transformers initially came about from NLP research or text research, they didn't particularly have to be limited to text. So, for example, people started applying them to images, and it's done in a fairly similar way to how you would apply it to text. That is, as I was showing you, that you take a particular piece of text and you mask it. So you remove certain words and ask the model to predict the word that is missing. In a vision transformer, what you do is you break an image into smaller bits. So in this case, for example, you can see that the image is broken into 3x3 patches. And you remove one of the patches randomly and ask the model to predict the missing patch. And if you train enough, you learn that the transformer is able to learn the elements of images just as it was able to learn about text earlier, and it's actually able to do it much easier than it's able to learn text. So one thing that might surprise some of the people here is that text models are much more heavier than image models. So the number of parameters required to have a very realistic text output is often in the tens of billions or at least hundreds of billions. Like for example, good text models are, let's say, 30 to at least 30 billion parameters long. Otherwise, the output can be choppy at times, and you would know that it is not human generated. Whereas image models can be fairly small. So a model like DALI 2, I think, was just a billion parameters or so, and those number of parameters are able to generate fairly accurate images. And one way in which you might be able to intuit that this should be the case is that we are much more forgiving when when an image is slightly off. So let's say the image that is generated, if a few pixels were different or the color was slightly off, you'd barely detect it. You'd still be able to tell a dog is a dog, even if some parts of the dog were misplaced. But in a text, even if a particular character goes from, let's say, an A to an I, you would know that it's a typo or it's a mistake and so on. So so we require far more accuracy from text models than we do from image models. So the number of parameters correspondingly is much more in text models for a similar level of being convincing that we would like. Okay, so finally, I'm coming to an end of my talk. So what happens in the future? So one thing, as I was mentioning before, is that we are running out of large-scale data to train a lot of models on. People have already tapped out as much text data as they could. Image data is getting close to getting tapped out. So the big future frontier is videos. Google and others are particularly looking to tap into the huge corpus of video data that's been uploaded into places like YouTube and so on to train. The idea is that you feed a huge amount of video data, and the model would not only be able to learn about creating videos, but also be able to figure out things like physics and so on just by watching the data sets. And it does seem that some of it is possible, of course, not everything, but models are able to convincingly recreate things like splashing water drops or bouncing balls and things like that reasonably convincingly. So there is a lot more to be done. Essentially, like video is a huge underexplored resource, I would say. So that's about it. So yeah, thank you. And I'd be happy to take any questions there. We have about 10 minutes, I think.
Hello, Farhad. I have a question here. So this is regarding the diffusion process, which you mentioned. So noise is injected in that process. And and you said that other than the Gaussian noise, other kinds of noises have also been tried, like Poisson noise and all. Now, my question is, so when you try different kinds of noises and you compare the results, how does it depend on the power spectrum of the noise? So like white noise versus red noise, has that been tried, or does it affect the results, or not at all, or any ideas?
I'm not sure. I've not looked at that. I would have to look it up and see what how different kinds of noise vary the output from the model. I do remember reading that certain kinds of noise produce better images of for certain domains. So for example, like the idea was that if you add the kind of noise that the model is trying to physically represent, it would do a better job, and we don't need to be restricted to Gaussian noise itself. Given that it's been a year and this idea hasn't taken off significantly, I suppose I suppose that it isn't meaningfully better. So maybe it was just a digression and it didn't take off. Maybe there are other reasons why it didn't take off. For example, computational complexity or something like that, given that Gaussian processes are very easy to set up in computer code and model in GPUs and so on. So there might be other reasons, but
Yes,
I don't know.
Yeah, I understand. So the Gaussian process can be, it need not necessarily be white, right? So there could be correlations in time and all that. So that was what actually I was wondering. But anyway, thank you. So I can also try to look up some of the works. Thank you. Farhad, I had a kind of question regarding the ethics of building one's own large language models. I mean, you said that anyone can actually build a LLM these days without the restrictions that are there in the closed source models. But so some of those restrictions have been put in place for a reason. So given that if you build your own LLM and release it in the open, you can do kind of sort of unethical things. Does that worry you?
Not very much, to be honest, partly because, it is a possibility that you could do it. But like you're right that some of the things that like OpenAI or other models that have been released publicly try to minimize. Like, for example, if you ask the model, how do I create a pipe bomb? It will tell you no. So, but if somebody is determined enough, those kind of things, because the models have been trained on internet data, they are available out there. So it's a matter of how determined you are. It does make it easy, but the other part that sort of cancels out for this is that models often hallucinate. That's something that I didn't talk about at all. And what is hallucination? That is essentially outputting, confidently outputting things that are not correct. Um, so you are unlikely to be able to take many of these things at face value and still be successful. One part that it does make it like the ethics of certain things, like for example creating bots that mimic humans. So in that case it is possible that people can be swayed by bots. People are in general not as discriminative as some of us might assume them to be. And I'll go a brief digression into one of the cases that happened very recently. Maybe some of you might have read about it. There is a company called Character.ai. And what Character.ai does is it creates these bots that are essentially personalized to a person. So you can develop a relationship with a bot, and that particular bot remembers what conversations you've had previously and so on. And they even market them as like your virtual boyfriend or girlfriend and so on. And what they found was that people started having fairly raunchy conversations with their bots and so on. And as every company, they wanted to at some point go public and so on. And they thought that given the kind of conversations their clients were having with their bots, this was a risk to the company. So what they did was they updated the models so that the models were not as likely to like basically not be as not safe for work. So they were less likely to respond to raunchy requests from their clients and so on. And what they found was that a lot of clients, or almost all of them, reacted extremely negatively to that kind of a change, where some of them said that it felt like their partner had died, or that they were extremely sad because the other person is, and they talked about them as if they were persons, is not responding to them as they were before. They're not as loving and so on. And this indicates, I mean, I think at some point there would be some kind of regulation that would come in. So, like for example, people who believe that they have these partners, virtual partners, and so on. And we see things like, for example, what would I call it? The fishing industry, where people convince particularly seniors to hand over their financial details or things like that. These bots can be good enough to be very convincing, very empathetic. I mean, they can be far more empathetic than humans can be, because a bot trained to be empathetic has no limits about, validating you all the time, regardless of how destructive or how unreasonable you're being and so on. So yeah, it's an ethical minefield. I don't delve into it very much, but it is a concern. At some point, I think we would have some level of regulation over consumer bots. There is one company that I know that is marketing a model which says that it can bring your loved ones back from death. That is, you give it a set of conversations that you had with somebody who has died, and it will train its model, and you can have a conversation with somebody who has died. And now this is something that creeps me out quite a bit. So you're right that this is there. I don't know what kind of regulation would it be? And in general, I'm less likely to approve of regulation before something has happened than after it has happened, because there are calls that AI research be stopped for a certain period of time, or we have limits on the kind of models that can be developed. And even India recently tried that all large language models should be approved by the government before they're deployed, and then they went back on it and so on. But yeah, there is a lot of back and forth on this particular part.
I had another question. So, you mentioned hallucination, and this is something that we have encountered a few times. So, kind of a couple of years back, Pranay Goel at Izer told me about this possibility of using bots to write scraps of code in Python and so on. And so I mentioned this back in my institute, and some of my group actually tried it out, and they told me that many times it will confidently output a code which actually is not correct at all. So, isn't this kind of a, big problem where you don't know whether to trust, uh, the output? So, like part of the reason why you're using it is so that, you can use something which is usable. So,
E- So there are different parts to this. Like when you want something factual or so on, like when you want something creative, hallucination is a sort of asset. Like if you're trying to write a novel and you want to flesh out a character, that's perfectly fine. Like what we call hallucination is essentially like answering correctly or incorrectly for the model is not any different. One part is not any different from the other. It's not like one is correct and one is hallucinated. It's just that it's a series of probabilities of certain tokens being generated. And that is all there is. So if it says like the capital of India is Washington, it's just that the model's parameters might have, I mean, the output probability of Wash was higher than the output probability of, say, Delhi. So, in general, the way in which you combat hallucination is two ways. One is you make sure that the correct training data is so much that it overwhelms anything else. In terms of what you encountered on coding, that is definitely there, and I've encountered it a lot as well. And particularly when you're trying to automate tasks, like not just write code, but let's say make API calls to do certain things, these models will happily create API calls that don't exist at all. And sometimes I'll create a correct API call, but in case data is missing, it'll fill it with something that is sort of okay, but maybe not what you wanted. And that can be very dangerous when these APIs are, let's say, performing a certain task. Like let's say uh, if it's been like let's say you have an API call to transfer a certain amount of funds from one account to another, and it wasn't specified what the other account would be, or maybe the other account is wrong. In that case, the model hallucinates and puts in something that should not be there. So you could have a fund transfer that goes to an account that does not exist. So things like that are concerns. So some of it can be combated by like not being completely trusting of a model's output. So you can see like, and this is again, if you look into research papers and search for things like as a large language model, I'm not allowed to, you'll find huge numbers of papers that have phrases like these, which indicate that these papers were not only written by ChatGPT, nobody even reviewed them. The reviewers didn't read them. The writers themselves did not read them, and things like that. Or other kinds of telltale phrases that indicate that a large language model has been used to write something. Particularly, another part that has been there is people tried using a large language model to diagnose certain things. And the good part about that is that it appears to be very accurate. You have an empathetic doctor that listens to all your complaints and provides you a diagnosis and so on. But then they found that regardless of what you did, like for example, recently somebody gave the MRI of a fish to different large language models which could accept multimodal input. And the model confidently went ahead and said that this is the cervical section of a human and this person suffers from so and so and so on. Except for one model, I think Gemini had it in its training data where it said that this is a MRI of a salmon. So you have to be you have to be aware of the fact that these models are not infallible and are not only not infallible, they can go wrong severely or marginally. And coding part is certainly right. Like the VAE, the variational autoencoder that I showed in this talk was generated using ChatGPT, but or large parts of it were generated using ChatGPT. But I had to iterate over it multiple times to get it completely correct. Now, I could have written the code myself, but I thought I'd just use it. And once you start using it, you don't feel like, I mean, it's like correcting somebody else's code. You feel like you don't want to deal with it. So what I did was kept feeding it back, like kept feeding the errors back into ChatGPT. And at least with larger context windows, like the amount of data you can give it and the fact that it stores previous interactions, it was able to correct each of the errors that it was getting until it finally got a running version that I presented in this talk. So yeah, like be aware that models hallucinate, all models hallucinate to varying degrees. And also another thing that at least for users, I would say is that for many questions that you might put to a large language model, the models have a certain like as you said, a particular political view in mind. And often most of the public models that you have, like ChatGPT or Bard or Gemini or Anthropic's Claude, they are all extremely left of center. So when you're asking questions about economic policies or things like that, it comes with a certain viewpoint, which you need to correct for, and be aware of that this is not a centrist opinion. This is not, like, it's very hard to get, let's say, a right of center opinion from a large language model, a public large language model. So just be aware of these kind of things.
Hi, Farad. So slight change of topic maybe. So you were talking about GANs and their problems. So I've been looking at some of the literature on generating synthetic tabular data, and the argument, or one of the motivations, well, there are two possible motivations. One is to generate larger. So for example, in biomedical applications, predicting patient outcomes and so on, one issue is that it's very hard sometimes to publicly share this data. And so if you can share equally good fake data, then that would work. So there is a program called CTGAN, for example, that does that, and a few others. They all date back to 3-4 years back. And we found they didn't actually work terribly well, as in, and I was just wondering, do you think this is, I was a little bit skeptical in particular of, can you really improve the performance of a machine learning model by just dumping a large amount of synthetic data on it, which is itself generated from a smaller quantity of real data? Because that seems to be the motivation in some of the papers I've read.
Yeah.
And secondly, can a synthetic data set approach the quality of the real data set in terms of you train a model on one or on the other? They both do equally well on held out real data.
Yeah, great question. Yeah, great question. So one part is true that CTGAN is something that I was aware of, partly because I looked into it for exactly the same purpose, for trying to see if it can mimic tabular data well. And for some cases it works, but if your data has a lot of categories and so on, I think it doesn't do as well. So it's possible to improve some of this. Now, the question of whether your data is good, whether synthetic data can be made good enough to be as good as real data, so that you can, for example, train models on or use it to augment limited amount of training data, is a hard question. It depends on your use case. And in some cases, like for example, let's say some of the use cases I've seen, let's say a bank wants to release a certain amount of data for modeling to other people where it does not want to share real data. This can often be done reasonably well because, let's say, transactions are often of a certain size. And as long as your training data is large enough, you might be able to approximate it well enough. In cases where you have things like location data and so on, this can be much more messier because it's data that does not follow a good distribution. So it may not be able to mimic it that well. Overall, question of whether synthetic data can be as good, it depends on what is the end goal that you're looking at. Like, it can sometimes be used to generalize a model. If your model, I mean, if you're dealing with small amounts of data, it can and does help with generalizing, like even essentially certain kinds of data augmentation techniques. Like, let's say you take an image, and to create more images, you might rotate an image or take the mirror image and things like that. Those are fairly simple transformations and would increase the amount of data that you have at some expense of generalization, but hopefully it would still end up with a better model than what you started off with without any augmented data. But other parts where it can be more dangerous when it comes to medical applications and so on. Like, one part that worries me sometimes is that a fairly large amount of training data for self-driving cars and so on comes from data generated using games such as Grand Theft Auto or similar simulators. So what they did was they generated training data from either people playing those games or just running those games through a simulator, and then used it to train those models. So now, depending on how good the various components of the models in those games, of the models that are used to generate the characters and images in those games are, your models that are being used to train, say, models that are going to be behind the operations of a self-driving car would be there. So we trust our lives to these models, but as to how good they are, I don't know. Like, as in, I can't quantify it. It's certainly better than nothing in some cases. If like, I would like to take a strong look at each of the data sets generated to see whether the distributions are actually as good as the original distribution that you started off with. And sometimes even eyeballing the distributions can tell you that the GAN hasn't learned it that well. GANs particularly are not as good at sometimes understanding the distribution due to things like mode collapse or not having enough, I mean, for tabular data and so on, sometimes there may just not be enough variety in your data set for it to learn the distribution well. And even in case of images, you require a fairly large number of images to be able to generalize well. So that's why for GANs, unlike diffusion models, GANs tend to work within a certain domain. So you would see GANs for, let's say, faces or bedrooms and so on, but not a generic, like there is no GAN for taking a caption and generating an image corresponding to that, because a GAN would not be able to do that very effectively. Maybe, I don't know, maybe that's a good topic. Like, would you be able to create something like a diffusion model for tabular data? I don't see why it should not be possible. It should be possible, and maybe it might do better. And did I answer your question?
Sorry, I didn't have the mic. Okay, yeah. No, you did. And clearly it's an open topic. And I was also thinking, can diffusion models do better in this case? And I think like 2 years back, I have seen a GAN-based image generator that was floating around as a Colab notebook. This was before or around the time DALL-E and all were becoming big. Probably diffusion models do better, but I thought GANs originally arose with that motivation, like being able to generate images with just a verbal description kind of thing. Might be wrong.
So they're able to generate images for a particular class of images, but not generic descriptions. Like, for example, with diffusion models, and like, for example, for DALL-E, you can give a caption like, make me a cat smoking a cigar like Sherlock Holmes set in 18th century England or something like that, and it would be able to do a convincing job. I don't think a GAN would be able to do anything close to that. Like, it would be able to do it for a particular class. Like, you can have a cat, you can have a cigar, you can have maybe a cat smoking a cigar, but all of those together would become less and less likely. But since you brought up Colab, I wanted to tell all the students here particularly that Colab is a great resource for trying out many of the models that you may not be able to on limited computational resources. So I've experimented with many of these diffusion models or GANs, image generation GANs, which require, let's say, a GPU, with doing it on Colab, and you can get pretty interesting results. You can experiment with them. You can see what happens with when you change parameter sizes, or what kind of outputs you can get, and so on. So yeah, like, thanks for bringing Colab up, but Colab is a great resource in case you don't have your own like extreme compute resources that sometimes larger models require.
Okay, thanks for it.
Thanks a lot, Farhad. Really appreciate you, remaining awake so late in the night to give us these talks. And I very much hope that the next time you're here in India, do please visit us in person. So
Thanks.
let's give Farhad a big hand for his lectures.